You've probably heard the saying in machine learning, more data is better data. And you know what? For the last decade, that single idea has fueled a revolution. It's made our algorithms incredibly powerful. But what happens when more data just becomes, well, too much? Today, we're going to dig into the smart way to scale and how to avoid some of the massive headaches that come with big data.
This quote, it's practically a mantra in the machine learning world. And it really gets at a fundamental truth. For a lot of problems, a kind of simple algorithm that's fed a ton of data will almost always beat a super brilliant algorithm that only gets a little. This is exactly why companies have been in this frantic race to collect as much data as they possibly can.
And this chart right here, it illustrates the point perfectly. This is from a classic study that was just trying to tell the difference between confusing words, like two, and two. But just look at what happens. As you feed it more and more data, that's the axis along the bottom, the accuracy of every single algorithm just shoots up. This is the big data dream, right there in action.
So the answer's simple then, right? Just get more data? Well, this is where that beautiful dream kind of smacks into a pretty harsh reality. Because the promise of big data also comes with a huge computational cost.
Let's put a number on it. Let's talk about a training set with 100 million examples. And look, this isn't some crazy made-up number. If you're doing something like analyzing US census data or tracking all the traffic on a big website, your training sets can easily have hundreds of millions of records.
Okay, so at the very heart of how a lot of these models learn, there's this algorithm called gradient descent. The best way to think about it is like a hiker who's trying to find the absolute bottom of a valley, but it's super foggy. All it can do is take a small step in whatever direction is steepest downhill. But here's the problem. To figure out which way is down, it has to look at the entire dataset. You see that big kind of funky E symbol on the screen? That's a summation sign. That's the part that says, look at everything.
And that right there is our huge bottleneck. For the algorithm to make just one single tiny update, one tiny step in its learning journey, it has to do a calculation that sums up information from all 100 million examples. It's just incredibly, painfully slow, and super expensive computation. So, this brings us to the big question. Is the only option to just keep throwing more computers and more money at the problem? Or is there maybe a more intelligent, more strategic way to go about this? Turns out, the answer isn't just about more computing power. It's about having a smarter strategy. And it all starts with a surprisingly simple sanity check. Before you even think about training on 100 million records, we're going to see if we can get a little sneak peek of how it might turn out. What if, instead of wrestling with that whole giant dataset, you just took a tiny, random sample of, say, 1,000 examples? Could that small sample really tell you anything useful about how your model is going to perform on the full, massive dataset? I know, it sounds a little crazy, right? How can a sample that's 0.001% of your data possibly tell you whether you should spend weeks or even months building the infrastructure to handle all of it? Well, the answer lies in this fantastic diagnostic tool. The secret, it turns out, is to plot something called learning curves. By training your model on just that small 1,000 example dataset and then watching how it performs, you'll see one of two very distinct patterns emerge. And those patterns, they're going to tell you everything you need to know about what to do next. So these patterns point to two classic problems in machine learning. On the left, you've got high bias. Just think of this as your model being way too simple for the job. It's like trying to fit a straight line to a really complex, curvy set of data. It's just not going to work. Then on the right, you have high variance. This is the opposite problem. Your model is too complex. It's so flexible that instead of learning the general trend, it just memorizes every single data point, noise and all.
Okay, so let's imagine the first scenario. You run your tests on the 1,000 examples, and the learning curves look like this. Both the error on the training data and the error on new data are high. And what's really important is that the lines have basically flattened out. They're not getting any better. This is the absolute classic sign of high bias. And here's the bottom line. In this situation, adding more data is a complete waste of your time. Your algorithm is just too simple to learn from the data it already has. Shoveling millions more examples at it won't fix that fundamental problem. And just like that, you've saved yourself a massive amount of work.
All right, but what if you see something completely different? What if your curves look like this? Now, the training error is super low. The model has perfectly memorized that little data set. But the error on new data it hasn't seen before is way up high. And that huge gap between the two curves, that's everything. It's the classic signature of a high variance problem, or what we usually call overfitting. And this is the green light we've been looking for. This gap is telling us that our model is definitely complex enough to learn. It's just overfitting because it has so little data. So the cure for this problem is exactly what we wanted to do in the first place: get more data. In this case, scaling up to your full 100 million examples is absolutely the right move.
See, that simple little 1,000 examples sanity check does more than just save you time. It gives you a crystal clear, actionable game plan for what to do next.
It really is this simple. If your learning curves come out looking flat, you know you have high bias. Your next move isn't to get more data. It's to fix the model itself. Try adding more features, or if you're using a neural network, add some more hidden units. But if you see that big gap, that's high variance, and your next move is clear. Go for it. It is absolutely worth the effort to scale up and use all that big data.
And really, that's the core idea here. In this world of massive scale machine learning, the most valuable skill isn't just being able to wrestle with huge datasets, it's knowing when that struggle is actually going to pay off. It's the difference between just working hard and actually working smart. So just think about that. With a tiny sample and a simple chart, you now know if it's even worth it to spend months scaling up your data. But okay, once you get that green light, what's next? How do you actually handle that 100 million record problem without waiting forever? Well, that's where really powerful techniques like stochastic gradient descent and MapReduce come into play. And we'll break those down next time.